In any system that handles real traffic, one server is never enough for long. This video is about load balancing, the mechanism that spreads incoming requests across multiple instances of a tier, keeping your system fast, available, and able to grow. By the end, you will understand how it works, why it matters, and when to reach for it. Imagine your web application launches and traffic triples overnight. Your single server is pegged at 100% CPU, requests are timing out, and users are leaving. You can upgrade that one machine scaling up, but there is a hard limit to how far that goes. The real answer is to run multiple instances of your server and split the work between them. But that raises an immediate question. How does a request know which instance to go to? Think of a busy airport check-in hall. When only one desk is open, everyone queues there regardless of how long it takes. The moment a coordinator opens 10 desks and starts directing passengers, shortest queue, next available agent, the whole hall flows smoothly. A load balancer plays exactly that coordinator role for your servers. It stands in front of a pool of instances and steers each arriving request to the right one. Here is what load balancing looks like inside a 3-tier architecture. The 3 tiers are the presentation tier, your web servers that render pages or serve API responses; the business logic tier, your application servers that process rules and decisions; and the data tier, your database. A load balancer sits at the entry point of each horizontally scaled tier. The client never speaks to a server directly. It speaks to the load balancer, which then chooses one of the available instances and forwards the request there. Let us trace a request step by step. The client sends its request to a single stable address, the load balancer. The load balancer applies a routing algorithm to pick an instance, maybe the next in rotation, maybe the one with the fewest active connections. Before forwarding, it confirms that instance is healthy. The request lands on a web server, which in turn calls the application tier load balancer, and so on, down through the tiers. Each tier is scaled and routed independently, which is the key architectural consequence. You can add or remove instances at any tier without the client ever knowing. Load balancing is not free. The balancer is a new component you must operate, monitor, and make highly available. Otherwise, it becomes a single point of failure itself. It also complicates session state. If a user's second request lands on a different server from their first, that server may not have their session data. You solve this with stateless design or shared session stores, but those are extra decisions. For a small internal tool, this overhead is rarely worth it. For a public-facing service with real traffic, load balancing is almost always essential. Picking an algorithm depends on your workload. Round-robin works well when requests are roughly equal in cost. Least connections is smarter for requests with wildly different processing times. A slow request does not starve others. Consistent hashing is valuable when you need the same client to always hit the same instance, for caching reasons, for example. Whatever algorithm you choose, always configure health checks, so the balancer automatically removes a failing instance from its pool. And before anything else, design your instances to be stateless. That single decision makes every other load balancing concern dramatically simpler. To bring it together, a load balancer is the component that lets you run many instances of a tier and spread work across them. You pick a routing algorithm that fits your traffic pattern, configure health checks so failures are handled automatically, and most importantly, make your instances stateless so any request can land anywhere. With those pieces in place, each tier in your architecture can scale horizontally, independently, and without downtime.